This material has been excerpted from the college television course, The World of Chemistry, and re-edited for use in the high school curriculum. The World of Chemistry is funded by the Annenberg CPB project. Additional funding provided by Dow, the Great Things Company, leaders in the world of chemistry, the 8,000 scientists of the Eastman Kodak Company, and the Exxon Education Foundation. This adaptation is supported by a grant from the National Science Foundation.
Metals seem to be everywhere. They form the superstructure of our cities. We can make cars, rings, and refrigerators out of them. But what do we know about metals? What is it about metals that makes them so useful and valuable? What is there about their makeup that gives metals their properties of luster, conductivity, ductility, and malleability? And where do they come from? Civilization has been shaped with metals. Metal machines make metal products. Products that we wrap in metal, ship in metal, and use every day. Even food comes sealed in metal. We use metals to generate electricity, and then we transmit it across the country in metal wires. We make crowns with them, and coins with them. Of course, it's not surprising we have found so many ways to employ metals. About 3/4 of all known chemical elements are metals. The most abundant in the Earth's crust are iron, aluminum, as well as calcium, sodium, potassium, and magnesium. There seems to have been a direct relationship between the metals we used, how we used them, and civilization. Human progress was even marked in terms of stone, bronze, and iron. As our needs become more sophisticated and our abilities to produce metals and alloys become more advanced, our uses of metals become more specialized and diverse. What is it about metals that makes them so useful? They conduct heat and electricity, and they're malleable and ductile. They can be pounded and drawn into many shapes. These are physical properties which can be explained by the metallic bond. Metals are crystalline solids. The atoms are held together by a metallic bond, which occurs when a valence electron from one atom feels the attraction of the nuclei of the neighboring atoms. It leaves the original atom, briefly attaching to the next atom. It then moves to another, and yet another. Electrons from every atom can move freely through the lattice of the crystal, not belonging to any one particular atom, and yet belonging to them all. We say these electrons are delocalized. We can picture the metal structure as a close-packed arrangement of positive metal ions immersed in a sea of negative electrons. This freedom of electron movement enables metals to carry an electric current. When we apply an external electrical field, the delocalized electrons drift from the negative to the positive side of the field. Delocalization also explains the ability of metals to conduct heat and reflect light. Metals are malleable and ductile because of the metallic bond. The non-directional attractions of each positive metal ion for the surrounding sea of electrons allows the atoms to slip by each other easily. But how exactly do we get metals from the Earth? And what has to be done so we can put them to use? Iron is one of the world's most well-known and useful metals. The most common way of obtaining iron from the Earth is open-pit mining, like this in Australia. If it is commercially feasible to extract the metal from the mineral mixture, we call that mixture an ore. Most iron ores are oxides. When a low-grade ore is mined, it must be physically separated from the other rocks and dirt. Only then is it ready to be shipped to a smelting plant where the metal will be extracted from its ore. Different ores have different requirements. The removal of iron from iron oxide in the ore known as hematite and the extraction of aluminum from aluminum oxide in the ore bauxite are examples of two different techniques.
In this experiment, I'm going to show you how we can extract iron from its ore, iron oxide, in the laboratory. I have in this little combustion boat about 1 gram of iron oxide. Let's see what happens when I run this magnet across it. It isn't attracted to a magnet. I'll put the iron oxide in the little tube, turn on the hydrogen. I'm going to light this end of the tube. There. And now we'll add a little heat to speed up the reaction. It's going to take about 5 minutes for the reaction to be completed. Well, I hope it's cooled enough by now. Let me take it out so you can see the color change. Can you see it? Let's check its mass. Its mass decreased. Let's see what happens when we run a magnet across it. Look at this. It's attracted to a magnet.
The industrial method uses carbon instead of hydrogen. The process is done in a blast furnace like this. The furnaces are huge, 30 meters tall and 10 meters wide at the base. Iron ore, coke, and limestone are loaded into the top of the furnace. Then hot air, about 600 degrees Celsius, is forced through. As the carbon in the coke burns, the temperature rises even higher. Carbon monoxide produced by the burning coke moves up within the furnace, and both it and the carbon react with the iron oxides, reducing them to metallic iron. At these temperatures, iron melts and sinks to the bottom of the furnace. Can we extract aluminum from aluminum oxide in a similar way in the lab? Paula Heron.
Can we use this same experiment to extract aluminum from aluminum oxide? I have about 1 gram of aluminum oxide in this little combustion boat. I'll put it into the tube, turn on the hydrogen, and now we'll add a little heat. It's going to take about 5 minutes for the reaction to be completed. It's cooled down now. It looks as if the color hasn't changed. Let's take it out so you can see it better. The color hasn't changed. Can you see? Let's check its mass. The mass hasn't changed.
In the case of aluminum oxide, this chemical reaction simply doesn't work. Aluminum couldn't be obtained in our experiment because hydrogen just isn't strong enough to break the aluminum oxide bond. Aluminum has a great affinity for oxygen. It can even take it away from iron.
For this reaction, I've mixed some powdered aluminum and iron 3 oxide. This reaction is called thermite. It takes a lot of energy to get this reaction started. So I'll ignite it with a strip of magnesium, which burns at a very high temperature. Below is some sand to catch the hot product. This reaction is extremely exothermic. It's so hot, it melted one of the products. Here it is, a piece of iron. It used to be iron oxide. The aluminum had such an affinity for the oxygen that it pulled it away from the iron oxide and left just iron.
That aluminum oxide bond is extremely strong. How is it broken in the industrial manufacture of aluminum? Electricity, a lot of it, is needed. The process is called electrolytic reduction and is barely over 100 years old. Charles Martin Hall, an Oberlin College graduate fresh out of school, invented the process in 1889. Aluminum oxide is dissolved in a molten aluminum salt. The melt is then jolted with 130,000 amps of electrical current, reducing the aluminum oxide to metallic aluminum. The power requirements are enormous. One aluminum plant in Frederick, Maryland, uses nearly a fifth of the total output of the nearby Potomac Edison Electric Company. But recycling aluminum is more efficient. It uses only 5% of the energy needed to extract aluminum from the oxide. Pure metals like iron and aluminum are by no means the only metallic substances in everyday use. There are alloys, blends of two or more metals, or a metal and a non-metal, blends which provide special properties. In some senses, steel is an alloy, basically a mixture of iron and varying amounts of carbon. Steel. More than any other metal, it drives the economy of the modern world. Most commonly, steel is made by the basic oxygen process. A furnace is filled with pig iron, limestone, and scrap steel. First, the impurities are burned off with a blast of oxygen. Then carefully measured amounts of carbon are added, producing the steel, which is harder than iron. But how does the addition of small amounts of carbon make iron stronger? When you add small amounts of carbon to iron, as little as 1 part per thousand, the carbon atom, being smaller than the iron atom, fits into the interstitial spaces of the crystal. This small change in the structure of the iron crystal makes the slipping of the iron ions more difficult. That's why steel is stronger than iron. Stainless steel is one of the best known and most useful alloys of iron. The addition of chromium and nickel prevents corrosion and makes stainless steel useful for pipes, tanks, sinks, and even jewelry. Molybdenum increases hardness and durability. Magnesium aluminum alloys are used in airplane bodies. These alloys are strong but light in weight. Rockets and the space shuttle have to withstand extreme conditions of stress and enormous variations in heat. Superalloys like iron and nickel or iron and cobalt have been developed with just the right properties for these special uses. One of the major properties of metals is that they conduct heat and electricity. An exciting new development is in the field of materials for superconductors that work at the temperature of liquid nitrogen. Superconductors are perfect conductors. No energy is lost in conducting electricity. This superconductor can levitate a magnet. A model of the arrangement of atoms in a superconductor shows that it contains yttrium, a rare earth metal, barium, an alkaline metal, copper, and oxygen. Other rare earth metals are being investigated for use in superconductors and several different applications. Superconductors may be used to make better magnets, faster computers, and more efficient electric power lines. Superconductors could be one of the most exciting breakthroughs for the future.